This is Mars. What killed the red planet? 3.5 billion years ago, there existed a vibrant world within our solar system, a world adorned with rivers. Not mere channels shaped by glacial melt or seasonal frost, but genuine rivers. Broad, meandering, and sustained flows of liquid water that traversed hundreds of kilometers across a landscape of volcanic rock and ancient craters. This world boasted lakes that endured for thousands, perhaps even millions of years. It may have harbored an ocean that spanned much of its northern hemisphere, a vast expanse of water deeper than some of Earth's seas. Its atmosphere was thick enough to trap warmth and nurture rainfall. Clouds gathered in its sky, not the fragile wisps of a dying planet, but robust, cumulus-like formations that transported moisture inland from the edges of basins and the shores of a possible northern sea. When it rained on ancient Mars, it was genuine rain. Droplets of liquid water cascading from a real sky onto real rock, carving channels that remain visible from orbit 3.5 billion years later. Its magnetic field, generated by a swirling iron core, enveloped the planet in an invisible shield that deflected the harshest rays of the sun. This world was Mars. Today, Mars stands as a desolate relic. Its atmosphere is less than 1% as dense as Earth's, so thin that liquid water cannot linger on the surface for more than a fleeting moment before it either freezes or evaporates. The average surface temperature hovers around -60 degrees Celsius. The magnetic field has vanished, replaced by scattered remnants of magnetism frozen into the oldest rocks, like the fading echo of a light extinguished billions of years ago. The rivers have been dry for longer than any complex life has thrived on Earth. The lakes are mere empty basins of dust and rock. The ocean, if it ever existed, has vanished, some of its water trapped in ice beneath the surface and at the poles, while the rest has been stripped away into the void of space, atom by atom, by the relentless solar wind. Something extinguished Mars. Something transformed it from a world that could have nurtured life into the frozen wasteland it is today. And this transformation was not instantaneous. It unfolded slowly, relentlessly, and irreversibly. A death by 1,000 cuts, each one invisible, each one nudging the planet further from the brink of habitability. The saga of Mars is the tale of a planet that possessed everything necessary to become a second Earth, and lost it all. Understanding what went awry is not merely an academic pursuit in planetary science. It is a profound lesson in what renders a world habitable and how precarious that habitability can be. Now, after decades of robotic exploration, we may have unearthed the first evidence that Mars was not just habitable, but inhabited. In July 2024, NASA's Perseverance rover drilled into a rock within an ancient Martian riverbed and discovered patterns that, on Earth, are nearly exclusively produced by living organisms. Leopard spots, chemical signatures of metabolic activity, a potential biosignature, published in Nature in September 2025, peer-reviewed, contested, and utterly tantalizing. Tonight, we trace the demise of a world, from the rivers that once flowed to the silence that has taken their place, from the magnetic shield that safeguarded the atmosphere to the moment it faltered, from the solar wind that stripped away the air to the ice that remains entombed beneath the dust, and from the rock that may hold, sealed in a titanium tube on the floor of an ancient crater, the answer to the oldest question in science: were we ever truly alone? Be sure to subscribe, for there are countless more extraordinary cosmic stories waiting to be unveiled. To comprehend what killed Mars, one must first grasp what Mars once was. 4.5 billion years ago, when the solar system was still in its infancy, Mars was far from the desolate, frigid planet we recognize today. It was a warm world. Not tropical, mind you. After all, the Sun was about 25 to 30% dimmer than it is now, and Mars orbits at a distance 1.5 times that of Earth. but warm enough to support life. With a thicker atmosphere and a greenhouse effect in play, liquid water could flow freely across its surface. The evidence of this ancient warmth is etched across the Martian landscape, a story that geologists can decipher as easily as reading words on a page. Valley networks, branching, dendritic river systems that closely resemble those found on Earth crisscross the southern highlands of Mars. These are not mere flood channels created by a singular, catastrophic release of water. They are intricate networks, complete with tributaries and distributaries, formed by prolonged rainfall or groundwater flow over extensive periods. Dating back to the Noachian period, the first billion years of Martian history, named after Noachis Terra, one of the oldest and most heavily cratered regions of the southern highlands, these features reveal that water flowed across Mars long enough to sculpt its diverse landscapes. The Noachian represents Mars's golden age. Spanning roughly 4.1 to 3.7 billion years ago, this era was marked by peak volcanic activity, a dense atmosphere, and abundant surface water. It was during the Noachian that the valley networks took shape, lakes brimmed with water, and the delta at Jezero was formed. If life ever took root on Mars, it was most likely during this fertile period. Following the Noachian was the Hesperian period, approximately 3.7 to 3.0 billion years ago, a time of significant transition. Volcanic activity persisted but began to wane. The atmosphere thinned, and surface water became sporadic rather than consistent. Massive floods, outflow channels carved by sudden groundwater releases, created some of the largest channels in the solar system, including Carse Valles, which stretches over 2,000 kilometers. Yet these floods were episodic, not indicative of a stable, warm, wet climate. They marked the final struggles of a hydrological system that was gradually shutting down. The Amazonian period, spanning from 3.0 billion years ago to the present, signifies Mars's cold, dry decline. Over this vast expanse of time, which encompasses 2/3 of Mars's history, the surface has been predominantly shaped by wind, dust, and ice. While volcanic activity has continued at a reduced level, no significant surface water has flowed. For the majority of its existence, Mars has been the frozen desert we observe today. Countless lake beds remain, hundreds of them scattered across the planet. Craters with inlet and outlet channels reveal a history of water flowing in, pooling, and eventually draining out, sometimes over millions of years. Jezero Crater, where NASA's Perseverance rover is currently exploring, is one such ancient lake. It was nourished by a river that deposited a fan-shaped delta of sediment at its edge, a delta that can still be seen from orbit today, preserved in stone, a testament to the once flowing water. Mineral deposits, clays, sulfates, carbonates, are scattered across the Martian surface, each indicating the past presence of liquid water. These minerals are concentrated in the oldest terrains and carry chemical signatures of the water that formed them. Some clays require neutral pH water and prolonged contact to develop. Their existence suggests that Mars had not just water, but water that was chemically conducive to life, water in which, on Earth, microorganisms would flourish. And there may have been an ocean. The northern lowlands of Mars, an expansive flat expanse that spans nearly 1/3 of the planet, have led some researchers to propose that it could be the remnants of an ancient sea. Features resembling shorelines, discerned from orbital imagery, outline a remarkably consistent elevation at the juncture of the northern lowlands and the southern highlands. If this ocean existed, it would have harbored enough water to envelop the planet to a depth of about 137 meters, or, concentrated within the northern basin, a reservoir of water potentially hundreds of meters deep. The evidence stretches beyond mere geological formations. In 2013, NASA's Curiosity rover, stationed in Gale Crater, drilled into a mudstone known as sheepbed, and uncovered clay minerals that had formed in water with a nearly neutral pH. Water that was neither overly acidic nor too alkaline for life to thrive. The analysis also unveiled the presence of vital chemical elements for life: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, all contained within a single rock sample. The Curiosity team deduced that the ancient lake in Gale Crater represented a habitable environment, a locale where, had microorganisms existed, they could have flourished. In 2024, Curiosity's ground-penetrating radar confirmed that Jezero crater, the operational site of the Perseverance rover, once housed a deep lake. The radar identified sedimentary layers beneath the crater floor that aligned with lake deposits, the physical remnants of a body of standing water now buried under billions of years of dust and rock. Mars, 3.5 billion years ago, was a vibrant world characterized by rainfall, rivers, lakes, and potentially seas. Its atmosphere was sufficiently thick to sustain these features, perhaps between 0.5 to 1 bar, in contrast to Earth's current 1 bar. Carbon dioxide and water vapor contributed to greenhouse warming. Volcanic activity from the colossal Tharsis volcanic province continually replenished the atmosphere with CO2 and other gases. And above all this, protecting the atmosphere from the relentless onslaught of solar wind was a global magnetic field. This is what Mars possessed, and this is what it ultimately lost. The magnetic field was the first to vanish. Its disappearance set off a chain reaction that altered everything. Mars, much like Earth, once generated a global magnetic field through a dynamo process, the convection of liquid iron in its core, driven by cooling and the release of heat from the planet's interior. This dynamo was active from the very dawn of Mars's history, at least 4.5 billion years ago, and produced a magnetic field comparable in strength to that of present-day Earth. Evidence for this comes from the southern highlands of Mars, where orbital magnetometers have detected extraordinarily strong remnant magnetization in the ancient crust, 10 times more potent than any crustal magnetization found on Earth. These rocks were magnetized by a powerful global field at the time of their formation, and they have preserved that magnetization for billions of years. However, the dynamo did not endure. For decades, the prevailing view held that Mars's magnetic field extinguished around 4.1 billion years ago, based on observations that large impact basins formed during the late heavy bombardment, such as Hellas, Argea, and Isidis, exhibited weak or non-existent magnetic signatures. The reasoning was straightforward. If these basins had formed while the dynamo was still operational, the newly exposed and cooling rocks should have been magnetized. Their lack of magnetization was interpreted as evidence that the dynamo had already ceased functioning. Yet, in 2020, researchers discovered clear magnetic signatures in the Lucas Planum lava flow, which formed less than 3.7 billion years ago, half a billion years after the dynamo was thought to have shut down. Then, in 2023, a study utilizing a quantum diamond microscope to analyze the ancient Martian meteorite Allen Hills 84001 revealed evidence of a strong magnetic field at 3.9 billion years ago, including possible indications that the field was reversing polarity, much like Earth's field does today. A 2024 study published in Nature Communications offers a compelling new perspective. The large impact basins on Mars may not be demagnetized due to a dormant dynamo, but rather because the dynamo was in a state of reversal. If the cooling rocks within these vast basins recorded alternating magnetic polarities as the magnetic field oscillated, the signals could effectively cancel each other out when measured from orbit, resulting in an apparent weak net magnetization. This suggests that these basins may have formed while the dynamo was still active and reversing, not while it was inactive. If this interpretation holds true, it implies that Mars's magnetic field could have persisted until as recently as 3.7 billion years ago, or even later, a timeline significantly longer than previously thought. This revised understanding carries profound implications for the planet's habitability, indicating that Mars had a protective magnetic shield during much of the time when rivers and lakes were present on its surface. However, the dynamo eventually ceased operation. Mars, being smaller than Earth, roughly half its diameter and 1/10 its mass, has a higher surface area to volume ratio, which enables it to lose heat to space more efficiently. Over time, the core cooled, weakening the convection that powered the dynamo until it ultimately stopped. The liquid iron in the outer core may have solidified, or it may have become too stable and stratified to sustain the vigorous convection necessary for a functioning dynamo. There may have been a catalyst, a catastrophic event that accelerated the cooling of the core. Some researchers suggest that the massive asteroid impacts during the late heavy bombardment could have disrupted the thermal structure of the mantle, injecting heat that acted as an insulating layer around the core, thereby reducing the temperature gradient required for convection. In this scenario, the very impacts that scarred Mars's surface may have also extinguished its magnetic field. Regardless of the cause, the outcome was the same. The magnetic field diminished, leaving Mars exposed. The remnants of this ancient magnetic field are still observable today. Mars Global Surveyor, which orbited the planet from 1997 to 2006, mapped the crustal magnetic field and uncovered a striking pattern. In the southern highlands, alternating bands of positive and negative magnetization stretch across the surface, reminiscent, at least superficially, of the magnetic striping found at mid-ocean ridges on Earth, where new crust is formed through seafloor spreading. This observation has led some researchers to propose that Mars may have experienced a brief period of plate tectonic-like activity early in its history, during which new crust was generated and magnetized by the reversing dynamo. Whether Mars ever had true plate tectonics remains one of the most hotly debated questions in Martian geology. If it did, that activity likely ceased very early, perhaps within the first billion years. Today, Mars is a one-plate planet, akin to Mercury and the Moon, its entire surface a single unbroken shell of rigid crust, cracked and faulted but never subducted or recycled. Without plate tectonics, there is no mechanism to return carbon to the atmosphere, no way to regulate the climate over geological timescales, no thermostat. This, as much as the loss of the magnetic field, sealed Mars's fate. The interplay between the dynamo, the atmosphere, and the climate forms an extraordinarily complex feedback loop. The magnetic field safeguarded the atmosphere. The atmosphere maintained the greenhouse effect. The greenhouse kept the surface warm. The warmth allowed water to remain liquid, and this liquid water, circulating through the crust, may have influenced the mantle's convection, which in turn affected the dynamo. When any link in this intricate chain broke, the entire system began to unravel. On Mars, the first link to break was the dynamo, and everything else followed suit. The solar wind is a relentless stream of charged particles, primarily protons and electrons, bursting forth from the sun's corona at astonishing speeds of around 400 to 800 kilometers per second. Here on Earth, our magnetosphere acts as a protective shield, deflecting the solar wind and safeguarding our atmosphere from direct erosion. In stark contrast, Mars, lacking a magnetic field, is directly exposed to this cosmic barrage, with the solar wind striking its upper atmosphere head-on. NASA's MAVEN mission, Mars Atmosphere and Volatile Evolution, was specifically crafted to delve into this phenomenon. Arriving at Mars in 2014, MAVEN has dedicated over a decade to unraveling the intricate dance between the Martian atmosphere and the solar wind, as well as the mechanisms by which atmospheric gases escape into the vastness of space. What MAVEN uncovered validated long-held theories. The solar wind is relentlessly stripping Mars of its atmosphere. Currently, this atmospheric loss occurs at a rate of approximately 100 grams per second, around a quarter of a pound. While this may seem trivial at first glance, the cumulative effect is staggering. Over billions of years, this loss becomes catastrophic. The process operates through multiple pathways. The solar wind carries a magnetic field that, upon encountering Mars's ionosphere, generates an electric field. This electric field accelerates atmospheric ions, charged atoms of oxygen, carbon dioxide, and other gases, propelling them to velocities sufficient to escape the planet's gravitational grasp. MAVEN discovered that about 75% of these escaping ions exit through Mars's magnetic tail, the downstream wake formed as the solar wind flows around the planet. The remaining 25% escape via polar plumes, columns of ions escaping from the planet's poles. However, the rate of escape is not uniform. During solar storms, such as coronal mass ejections and solar flares, the loss rate surges dramatically. MAVEN recorded a significant solar storm impacting Mars in March 2015, observing a tenfold increase in atmospheric escape. In the early solar system, when the Sun was younger and far more active, solar storms were both more frequent and intense, with the solar wind itself being 10 to 100 times stronger. Consequently, the atmospheric escape rate billions of years ago would have been orders of magnitude higher than it is today. Bruce Jakosky, MAVEN's principal investigator, likened this process to the gradual theft of a few coins from a cash register each day, individually insignificant, yet devastating over time. By employing isotopic measurements of argon, a noble gas that remains chemically inert and can only escape physically, Jakosky's team estimated that approximately 65% of all the argon that ever existed in Mars's atmosphere has been lost to space. This suggests that the total atmospheric loss has been monumental, sufficient to transform a once thick, warm atmosphere into the thin, cold remnant we observe today. Yet, the solar wind was not the sole culprit. Mars's diminutive size played a significant role in this atmospheric decline. Its lower gravity, about 38% that of Earth, facilitates the thermal escape of lighter gases like hydrogen. Ultraviolet radiation from the Sun breaks down water molecules in the upper atmosphere into hydrogen and oxygen, with hydrogen escaping readily. Over billions of years, this photochemical escape process has siphoned off a vast amount of water from Mars, not by evaporating it from the surface, but by dismantling it in the upper atmosphere and allowing the fragments to drift away into space. Some of the lost carbon dioxide became trapped in surface rocks through chemical weathering, forming carbonate minerals. However, unlike Earth, where plate tectonics recycles carbonates back into the atmosphere via volcanic activity, Mars lacks this geological dynamism. Once carbon is sequestered in the rocks, it remains there. The atmosphere continues to thin. The greenhouse effect weakens. The surface cools. The demise of Mars was not a singular catastrophe. It unfolded as a series of cascading events. The magnetic field faltered. The solar wind stripped away the atmosphere. The atmosphere thinned further. The greenhouse effect diminished. The surface cooled. Water either froze, sublimated, or escaped into the void of space. Rivers ceased their flow. Lakes evaporated. The ocean receded, ultimately disappearing. Thus, Mars transformed into what we see today, a frigid, arid, irradiated wasteland, where the atmosphere is so tenuous that the sky appears nearly black, even at noon. This transformation spanned approximately 1 billion years. It was not a swift disaster, but rather a prolonged decline, a planetary autumn that endured longer than the entire history of complex life on Earth. There was no singular moment when Mars shifted from being habitable to uninhabitable. Instead, the transition was gradual, marked by episodes of more rapid change. In the initial phase, as the magnetic field began to weaken, the effects were subtle. The atmosphere thinned slightly. Average temperatures dipped by a degree or two. Some rivers that once flowed continuously began to do so only seasonally. Lakes that had remained stable started to shrink. As the atmosphere continued to thin, the greenhouse effect weakened even further. Temperatures fell below the freezing point of water for extended periods. Lakes froze over. Rivers flowed only during the warmest seasons, nourished by melting ice. The Martian landscape shifted from a realm of persistent water to one of intermittent water. Still habitable, yet increasingly marginal. Eventually, atmospheric pressure dropped below the triple point of water, the critical pressure at which liquid water can exist. At this juncture, water could only exist as ice or vapor, never as a stable liquid. This marked the point of no return. Once the atmosphere thinned beyond this threshold, surface water became a physical impossibility. Any ice that sublimated could not recondense into liquid. The rivers did not merely slow and stop, they became physically impossible. The laws of physics simply no longer allowed for their existence. This final transition from intermittent water to a complete absence of water likely occurred around 3 billion years ago, give or take a few 100 million years. After this point, Mars's surface was eternally dry, eternally cold, eternally lifeless. From about 4 billion years ago, when the magnetic field weakened, to around 3 billion years ago, when the last significant surface water likely vanished, Mars underwent a slow, irreversible transformation from a potentially habitable world to a barren one. The window of habitability may have remained open for roughly 1.5 billion years, ample time, by Earth standards, for life to emerge and flourish. And then it closed, for good. Today, Mars is a realm of extremes and contradictions. Its atmosphere consists of 95% carbon dioxide, yet it is so thin, roughly 0.6% of Earth's surface pressure, that it offers almost no greenhouse warming. The average surface temperature hovers around -60 degrees Celsius, but it can plummet to -140 degrees near the poles in winter, or rise to a relatively mild 20 degrees Celsius at the equator on a summer afternoon. This temperature can be deceiving, however. The thin air means that warmth is felt only at the surface. Just a centimeter above the ground, the air temperature drops sharply. You could find yourself with warm feet and a frozen face. The surface of Mars presents a captivating dichotomy, divided into two remarkably distinct hemispheres. The southern highlands, ancient and heavily cratered, rise majestically, showcasing a rugged landscape that harkens back to the planet's formative billion years. In stark contrast, the northern lowlands are younger, smoother, and lie several kilometers lower, creating a striking geological divide known as the Martian crustal dichotomy. This feature is not only one of the most prominent in our solar system, but its origins remain a topic of intense debate among scientists. The elevation difference between these two terrains is approximately 5 kilometers, and the transition is often abrupt, resembling a geological cliff that encircles much of the planet. If the giant impact hypothesis holds true, the event that sculpted the northern lowlands would rank among the most colossal impacts in the solar system's history, overshadowing even the cataclysm that formed Earth's moon. The resulting Borealis Basin would stretch an astonishing 10,600 kilometers in length and 8,500 kilometers in width, encompassing about 40% of Mars's surface, making it the largest impact scar known to exist. This hypothetical impact is believed to have occurred around 4.5 billion years ago, within the first 100 million years of Mars's existence, predating the formation of many surface features we observe today. The southern highlands, with their ancient cratered terrain, represent the remnants of the original Martian crust that endured the cataclysm. Meanwhile, the northern lowlands signify the impact basin, which was later inundated by volcanic lavas and potentially by water. One theory suggests that a massive impact in the northern hemisphere early in Mars's history excavated the lowlands and created the elevation disparity. Another theory posits that internal geological processes, such as mantle convection or early plate tectonic-like activity, were responsible for this phenomenon. Dominating the Western Hemisphere is the Tharsis volcanic province, an immense bulge of volcanic terrain that rises 10 kilometers above the surrounding surface and spans an area comparable to North America. At its summit lie the largest volcanoes in the solar system. Olympus Mons, the tallest of them all, towers 21.9 kilometers above the Martian datum, nearly 2.5 times the height of Mount Everest. Its base is so expansive, measuring approximately 600 kilometers in diameter, that standing atop its summit would prevent you from seeing its edges. The volcano's breadth exceeds what the curvature of Mars allows a surface observer to perceive. The caldera at its peak, a nested complex of collapse craters, measures 80 kilometers across, ample space to accommodate a small city. The Tharsis volcanoes are shield volcanoes, akin to Hawaii's Mauna Loa, but on a vastly grander scale. Their colossal sizes can be attributed to the absence of plate tectonics on Mars. On Earth, tectonic plates shift, carrying volcanoes away from their magma sources, which limits their growth and results in chains of progressively younger volcanoes. Conversely, on Mars, the crust remains stationary over the mantle plume, allowing the volcano to grow continuously, sustained by the same source for billions of years. Olympus Mons may have remained active until as recently as 25 million years ago, a mere blink in geological terms. Some researchers even suggest that eruptions within the last 2 million years cannot be dismissed. If this is the case, Mars may still have future eruptions in store, although predicting when that might happen remains elusive. The Tharsis region is not just a mere collection of volcanoes, it is a structural feature of such magnitude that it has reshaped the entire planet. The immense weight of the Tharsis bulge has warped Mars's lithosphere, resulting in a network of radial fractures that extend thousands of kilometers in every direction. Valles Marineris itself is one of these fractures, a rift that emerged as the crust was stretched under the gravitational burden of Tharsis. The volcanic activity of Tharsis played a crucial role in shaping the evolution of Mars's atmosphere. Over billions of years, these colossal volcanoes released vast amounts of carbon dioxide, water vapor, and sulfur dioxide into the Martian atmosphere. In the planet's early days, when the atmosphere was dense enough to create a greenhouse effect, this volcanic outgassing likely served as the primary mechanism for keeping surface temperatures above the freezing point of water. However, as volcanic activity waned due to the cooling of Mars's interior and a dwindling supply of magma, the replenishment of the atmosphere slowed, tipping the balance toward atmospheric loss. Consequently, the atmosphere thinned, the surface cooled, and water began to freeze. The decline of Martian volcanism marked another critical failure in the chain of events that led to the planet's demise. Without ongoing volcanic activity, there was no source of new atmospheric gases to replace those stripped away by the solar wind. As a result, the atmosphere could only continue to shrink, and without a thick atmosphere, surface water could not endure. Then we have Valles Marineris, the largest canyon system in the solar system. Stretching approximately 4,000 kilometers along the Martian equator, it rivals the width of the continental United States. In some areas, it spans 200 kilometers across and plunges 7 kilometers deep enough to engulf Mount Everest with room to spare. Despite its name, Valles Marineris is not a river valley. It is a tectonic rift, a fissure in the Martian crust formed by the immense stresses of the Tharsis bulge. Yet water did flow through this canyon at various points in Martian history, and some of the layered deposits within may hold sedimentary records of that water. Mars's polar ice caps are fascinating layered structures composed of water ice and carbon dioxide ice. The northern cap is primarily made up of water ice, measuring roughly 1,000 kilometers across and up to 3 kilometers thick. The southern cap, while smaller, sits atop a massive deposit of water ice buried beneath a thin layer of carbon dioxide frost. Together, these polar caps and the subsurface ice deposits contain enough water to cover the entire planet to a depth of about 35 meters, a significant reservoir, though still far less than the volume suggested by ancient river valleys and potential ocean shorelines. So where did the rest of the water go? The MAVEN mission has revealed that hydrogen, the lighter component of water, has been escaping into space for billions of years. Some water has been trapped in hydrated minerals within the crust, while some may remain as subsurface ice or even liquid brine at greater depths. However, the prevailing conclusion is that most of Mars's original water has been lost, stripped away by the solar wind and photo-dissociated by ultraviolet light, molecule by molecule, over geological time. The D/H ratio, the ratio of heavy hydrogen to ordinary hydrogen in the remaining atmospheric water vapor on Mars, is enriched by a factor of about 7 compared to Earth's oceans, indicating a significant preferential loss of lighter hydrogen. This enrichment serves as a forensic fingerprint of water loss, similar to the evidence that suggests Venus lost its oceans. Yet, while Venus exhibits a D/H enrichment of 100 to 150 times that of Earth, Mars's more modest enrichment points to a different narrative. Mars lost less water than Venus, but did so more recently, and this process is still unfolding. How much water has Mars actually lost? Estimates vary, but isotopic evidence suggests that Mars once possessed enough water to cover its entire surface to a depth of at least 137 meters, and possibly much more. If the Northern Ocean hypothesis holds true, the original water, most of this water is now gone, fragmented by ultraviolet light, whisked away by the solar wind, or locked into minerals within the crust. What remains is but a fraction, preserved as polar ice and subsurface deposits. But even this remnant is extraordinary. The total estimated volume of water ice on Mars, found in its polar caps, shallow subsurface, and mid-latitude glacial deposits, stands at around 5 million cubic kilometers. To put that into perspective, the Greenland ice sheet on Earth contains approximately 2.85 million cubic kilometers. Despite having lost a significant portion of its water, Mars still boasts more ice than Greenland. Much of this ice lies buried beneath the surface. The Mars Reconnaissance Orbiter's radar has unveiled vast ice sheets hidden at mid-latitudes, some exceeding 100 meters in thickness and stretching for hundreds of kilometers. These concealed glaciers are remnants of bygone climatic eras when Mars's axial tilt was more pronounced, allowing ice to shift from the poles to lower latitudes. They are cloaked beneath a thin layer of dust and regolith, which insulates them from sublimation. The distribution of subsurface ice is not haphazard. It adheres to patterns influenced by latitude, slope orientation, and geological context. Near the poles, ice is ubiquitous, often just centimeters beneath the surface. The Phoenix lander, which touched down close to Mars's North Pole in 2008, revealed water ice simply by scraping away the topsoil with its robotic arm. The ice was so near the surface that it sublimated visibly under the Martian sun, vanishing within a few days. For future human explorers, this ice is not just a scientific curiosity, it is a vital resource. Accessible water ice could be melted and purified for drinking, split into hydrogen and oxygen for rocket fuel and breathable air, and utilized for agriculture in pressurized habitats. The presence of abundant near-surface ice at specific Martian latitudes has directly influenced the selection of sites for proposed human missions. Mars may be inhospitable, but it is not devoid of resources. The water is there, merely frozen, buried, and waiting. The dust itself is remarkable. Mars's surface is blanketed in a fine-grained regolith, pulverized rock rich in iron oxides that impart the planet's distinctive red hue. This rust-red color is, in fact, rust, iron that has oxidized over billions of years due to the planet's thin yet chemically reactive atmosphere. When this dust is lifted into the atmosphere by the wind, it casts a butterscotch tint to the Martian sky during the day and creates eerie blue sunsets, contrasting with Earth, where the sky is blue by day and sunsets are red. This color inversion arises from the differing sizes of scattering particles. Earth's molecules scatter blue light, while Mars's dust particles scatter red light, allowing blue to pass through. If you could visit Mars, standing on its surface and taking in the view, you would be greeted by a landscape of stark, desolate beauty. The sky would appear as a pale butterscotch during the day, tinged with blue near the sun at dawn and dusk. The ground would be strewn with rocks coated in fine rust-red dust. With gravity at just 38% of Earth's, you would feel light and buoyant. However, the air is composed of 95% carbon dioxide, rendering it unbreathable, and even at the warmest equatorial noon, the temperature would be lethal without a heated suit. The radiation, unshielded by a magnetic field, is intense. Mars is undeniably beautiful, but it is far from welcoming. Mars's thin atmosphere generates weather that is both familiar and alien. Wind speeds can soar to 100 kilometers per hour during dust storms, but due to the thin air, the force of these winds is akin to a gentle breeze on Earth. A hurricane-force wind on Mars would barely stir a flag. Yet, it can lift the ultra-fine Martian dust, particles just a few microns across, finer than talcum powder, and transport it around the globe. The global dust storm of 2018, which marked the end of the Opportunity rover's mission after 15 years, lasted for months and diminished sunlight at the surface by over 99%, depriving the solar-powered rover of energy. Mars is a planet that has gradually shed its layers. Its atmosphere, its water, its warmth, its magnetic shield, all have vanished or dwindled to mere traces. What remains is a world that holds within its rocks and landscapes a vivid chronicle of its former self. Deciphering this chronicle is the primary objective of the most ambitious robotic exploration initiative ever undertaken. Perseverance touched down in Jezero Crater on February 18, 2021. Its mission, the most scientifically ambitious ever dispatched to another planet, revolves around a singular question: did life ever thrive on Mars? The selection of Jezero was the culmination of a meticulous years-long process that evaluated over 30 potential landing sites. The choice was driven by the pursuit of astrobiology. The delta at Jezero was identified as the most promising location for preserved biosignatures, based on our understanding of how life is recorded in the geological history of Earth. The name Jezero is derived from a town in Bosnia and Herzegovina. In several Slavic languages, it translates to lake. The crater spans approximately 45 kilometers in diameter, and the evidence for an ancient lake is compelling. Two river channels breach the western rim of the crater, transporting sediment from the surrounding highlands into the basin. The resulting delta, a fan-shaped accumulation of layered sediment, is discernible from orbit as a striking geological feature. Ground-penetrating radar from Perseverance has confirmed the existence of deltaic sediments beneath the surface, showcasing the tilted, layered structure typical of a river depositing materials into a body of standing water. The lake at Jezero existed during the late Noachian to early Hesperian period, around 3.5 to 3.8 billion years ago, when Mars boasted a thicker atmosphere and possibly a magnetic field. the water was likely fresh or slightly saline, inferred from the mineral composition of the sediments. By any reasonable standard, the environment would have been conducive to life. Jezero was selected because it is an ancient lakebed, nourished by a river that formed a deltaic fan of sediment at the crater's western edge. On Earth, river deltas are among the most favorable environments for preserving traces of past life. Fine-grained sediments, clays and silts, ensnare organic molecules and microfossils, shielding them from degradation. The delta at Jezero is approximately 3.5 billion years old, dating back to a time when Mars had surface water and a magnetic field. If microbial life ever existed on Mars, Jezero's delta stands as one of the most promising sites to search for its remnants. Perseverance is equipped with the most sophisticated array of scientific instruments ever sent to the surface of another planet. Pixel, the planetary instrument for X-ray lithochemistry, employs an X-ray beam to analyze the elemental composition of rocks at the level of individual mineral grains. Sherlock, scanning habitable environments with Raman and luminescence for organics and chemicals, is capable of detecting organic molecules and mapping their distribution within a rock. SuperCam fires a laser at rocks and examines the resulting plasma to determine mineral and chemical composition. RIMFAX, the radar imager for Mars's subsurface experiment, looks beneath the surface, uncovering buried geological structures. Yet perhaps Perseverance's most crucial feature is its drill. The rover can core into rock, extract a cylindrical sample roughly the size of a piece of chalk, and seal it within a titanium tube for future retrieval. As of July 2025, 33 samples have been collected, intended for return to Earth by a future Mars sample return mission, where they can be analyzed with laboratory instruments that are far more sensitive than anything that could be deployed to Mars. In the summer of 2024, Perseverance was diligently surveying the Bright Angel Formation, a series of rugged outcrops lining the banks of Neretva Vallis, an ancient river valley approximately 400 meters wide that once channeled water into the Jezero Lake. The rocks within this formation are sedimentary, composed of clay and silt laid down by the ancient river. On Earth, these are precisely the kinds of rocks that excel at preserving traces of microbial life. The fine-grained size of clay and silt, along with their propensity to absorb organic molecules, makes them natural time capsules, encapsulating biological signatures within the rock matrix and shielding them from degradation caused by ultraviolet light, oxidation, and thermal alteration. From an astrobiological standpoint, a mudstone formed in a river represents one of the most promising environments to search for ancient microbial life. The fact that these mudstones date back 3.5 billion years, to a time when Mars boasted surface water, a magnetic field, and conditions suitable for life, adds to their allure. On July 18, 2024, Perseverance's cameras captured an image of a rock shaped like an arrowhead, measuring about 1 meter in length and 0.6 meters across, partially embedded in the ancient riverbed. The team affectionately dubbed it Chayava Falls. Its surface was adorned with spots. There were two distinct types of spots. The first were small, dark specks, akin to pepper grains, scattered across the rock, affectionately referred to as poppy seeds. Analysis using PIXL revealed these to be tiny nodules, ranging from 100 to 200 microns in diameter, rich in iron and phosphorus. Based on their chemical characteristics, scientists hypothesized that they were likely composed of vivianite, an iron phosphate mineral that, on Earth, typically forms in waterlogged, oxygen-poor sediments, often in conjunction with biological activity. The second type was even more eye-catching. Larger spots, millimeter-scale patches, lighter at the center with dark borders of iron-rich material, were dispersed across the rock's surface. The team named them leopard spots. On Earth, similar features in sedimentary rocks are predominantly formed through one of two processes: microbial activity or chemical reactions that can sustain microbial life. These spots emerge when microorganisms or chemical reactions reduce iron minerals, lightening the red, oxidized rock to a paler hue, while the reduced iron migrates outward and precipitates as a dark ring surrounding the bleached area. The result is a captivating pattern of light spots encircled by dark halos, the leopard spots. Perseverance also detected organic carbon within the rock using Sherlock, along with sulfur compounds. The combination of organic carbon, iron, phosphorus, and sulfur in a fine-grained sedimentary rock deposited by an ancient river in a habitable environment was nothing short of exhilarating. The Vivianite nodules, the poppy seeds, are particularly fascinating because, on Earth, the formation of Vivianite in sediments is closely linked to biological activity. Microorganisms that reduce iron, utilizing it as an electron acceptor in their metabolism, much like we use oxygen, commonly produce Vivianite as a metabolic byproduct. The presence of this mineral in a Martian sedimentary rock, formed by an ancient river in a habitable setting, is precisely the kind of evidence astrobiologists have been eagerly seeking. Meanwhile, the leopard spots bear a remarkable resemblance to features found in terrestrial sedimentary rocks colonized by iron-reducing bacteria. On Earth, these patterns, technically known as reduction spots or bleached halos, can be observed in red sandstones and mudstones worldwide, and their formation is well understood. Iron-reducing microbes consume the iron oxide that imparts the rock's red color, lightening it to a softer hue. The reduced iron then migrates outward and reprecipitates as a dark halo around the bleached area. The end result is a spot, a light center encircled by a dark rim that serves as a hallmark of biological iron reduction. Could the enigmatic leopard spots of Mars have emerged without the influence of biology? It's a possibility. The pure chemical reduction of iron can indeed take place when hydrogen-rich fluids, such as water, seep through iron-laden rocks. However, the Perseverance team rigorously tested this and other abiotic theories against their findings, only to conclude that none sufficiently accounted for the complete range of observations. The mineral compositions, the presence of organic carbon, the spatial arrangement of the spots, and their geological setting. Each of these elements is intriguing on its own. Together, they form a chemical toolkit essential for microbial life. Electron donors, electron acceptors, and the fundamental building blocks of existence. On July 21, 2024, Perseverance drilled into Chayava Falls, retrieving its 25th sample, which was sealed in a titanium tube and named Sapphire Canyon. The team dedicated over a year to analyzing the data. They explored alternative scenarios. Could the leopard spots have arisen solely from abiotic chemical processes? Might the organic carbon have arrived via meteorite impacts instead of being produced by life? Could the mineral formations have developed at temperatures too extreme for any known organisms? In September 2025, their findings were published in Nature. The peer-reviewed article indicated that abiotic explanations for the leopard spots were less plausible than biological ones, although they could not be completely dismissed. The authors noted that the combination of chemical compounds found in the Bright Angel Formation could represent a rich energy source for microbial processes. The language used was deliberate and measured, as it needed to be. No one was asserting that life had been discovered on Mars. Rather, they were making a more nuanced claim. They had identified a potential biosignature, a characteristic that might hint at a biological origin, but necessitates further investigation before any definitive conclusions can be drawn. NASA's acting administrator described it as the closest we have ever come to uncovering life on Mars. The project scientist deemed it a pivotal moment in the scientific journey. Meanwhile, lead author Joel Hurowitz from Stony Brook University stressed the importance of conducting laboratory analyses on the actual sample. analyses that can only take place on Earth, utilizing instruments not available on Mars. The Sapphire Canyon sample remains sealed in its titanium tube on the Martian surface, nestled within the Perseverance rover. It cannot undergo further analysis in its current location. To resolve the question it raises, whether the leopard spots were formed by Martian microbes or through Martian chemistry, the sample must return to Earth. The Mars Sample Return mission, designed to retrieve Perseverance's sample tubes and transport them back to our planet, is still in the developmental phase. Budget constraints, engineering hurdles, and political uncertainties have caused multiple delays and modifications to the mission. As of early 2026, no definitive launch date has been established. The samples lie in wait on Mars, their secrets locked away. The answer may already reside within the tube, yet it remains 225 million kilometers distant. The Mars Sample Return mission stands as the most intricate robotic space endeavor ever envisioned. The original blueprint, crafted collaboratively by NASA and the European Space Agency, included a lander that would collect the sample tubes stored by Perseverance, transfer them into a small rocket, the Mars Ascent Vehicle, which would then launch them into Martian orbit, where an orbiting spacecraft would capture them and ferry them back to Earth. The entire round trip is projected to take approximately a decade. However, the estimated cost, over $10 billion according to various analyses, and the intricate engineering challenges have generated ongoing political obstacles. Budget cuts, delays, and redesigns have continuously pushed the mission's timeline further into the future. Alternative strategies have been suggested, including partnerships with commercial entities and more straightforward retrieval methods. As we look ahead to early 2026, the way forward remains ambiguous. NASA has been investigating more streamlined, cost-effective options, such as utilizing commercial launch vehicles and developing smaller, more focused retrieval systems. The European Space Agency's Earth Return Orbiter, designed to capture samples in Martian orbit and transport them back to Earth, is still part of the foundational plan. Yet the timeline has faced repeated setbacks, with the earliest feasible return date for the samples now projected to be in the mid-2030s at best. The frustration within the scientific community is palpable. Perseverance has operated flawlessly, collecting dozens of meticulously chosen and scientifically characterized samples from the most promising astrobiological site ever identified on another planet. The samples are secured, the tubes sealed. The potential scientific breakthroughs that could arise from these samples, analyzed in laboratories equipped with advanced tools like electron microscopes, mass spectrometers, synchrotron radiation sources, and other instruments far more sensitive than anything on Mars, could answer questions that have lingered for centuries. Alarm bells are ringing within the scientific community. The Perseverance samples represent a unique, irreplaceable scientific treasure, the only deliberately collected, contextually characterized samples from an ancient habitable environment on another planet. If these samples are not returned, the critical questions they could address, regarding Mars's habitability, the potential for life, and the chemical evolution of a dying world, may remain unanswered for generations to come. Time is of the essence. Perseverance's mission is constrained by the lifespan of its nuclear power source, a radioisotope thermoelectric generator that will gradually lose output over the next decade. While the sample tubes, stored within the rover and in a depot on the surface, will remain intact for a longer period, the rover's ability to retrieve and load them is essential. Without it, the logistics of returning the samples become even more daunting. The irony is striking. Humanity has successfully designed, built, launched, landed, and operated the most advanced scientific instrument ever sent to another planet. This instrument has potentially uncovered the most significant scientific discovery in the history of space exploration. Yet, the greatest hurdle now is not technological or physical, It's a matter of funding and political will. The answer to whether we are alone in the universe may very well be sitting in a tube on Mars, awaiting the decision to bring it home. The question of life on Mars has captivated scientists for over a century. In the late 19th century, the Italian astronomer Giovanni Schiaparelli observed linear features on Mars, which he termed canali, channels. This term was translated into English as canals, suggesting artificial construction. Percival Lowell, an American astronomer, even constructed an entire observatory in Arizona to study these supposed canals, convinced they were the handiwork of an intelligent civilization striving to irrigate a dying world. In reality, these canals were mere optical illusions, artifacts of the human eye's propensity to connect disparate features into lines when observing at the limits of resolution. Yet the question lingers. When the Mariner missions reached Mars in the 1960s and unveiled a cratered, seemingly barren landscape, hopes for extraterrestrial life began to wane. The Viking landers, which touched down in 1976, conducted the first, and to this day, the only, direct biological experiments on the Martian surface, yielding results that were anything but clear-cut. One experiment, known as the labeled release experiment, produced a positive signal suggestive of microbial activity. However, the other experiments did not corroborate this finding. The scientific community, albeit with some discomfort, converged on the interpretation that the positive result stemmed from reactive chemistry in the Martian soil rather than any sign of life. Yet the debate remains unresolved. Gilbert Levin, the lead investigator of the labeled release experiment, held steadfastly to his belief until his passing in 2021, asserting that his experiment had indeed detected life on Mars. While most scientists disagree, the data from Viking continues to be genuinely ambiguous, a stark reminder that identifying microbial life, even with specially designed instruments at hand, is an extraordinarily challenging endeavor. The Viking missions imparted a crucial lesson that has influenced every subsequent Mars mission. Instead of seeking life directly, the priority should be to identify habitable environments, followed by the search for preserved organic molecules, and only then to look for biosignatures. This methodical approach, habitat, organics, biosignature, is the very strategy that the Curiosity and Perseverance rovers were engineered to implement. In 1996, a team led by David McKay at NASA's Johnson Space Center announced the discovery of features within the Martian meteorite ALH 84001 that they interpreted as potential evidence of ancient Martian life, structures resembling fossilized bacteria. This announcement captured global headlines and prompted President Clinton to convene a press conference. However, subsequent analyses indicated that these features could be attributed to non-biological processes, and the claim gradually lost traction within the scientific community. Nevertheless, the meteorite itself remains scientifically significant. It is the same sample that, decades later, provided magnetic evidence suggesting that the Martian dynamo persisted until at least 3.9 billion years ago. Curiosity, which landed in Gale Crater in 2012, discovered organic molecules within Martian rocks, complex carbon-based compounds that serve as the building blocks of life. Yet, it's important to note that organic molecules can also arise from non-biological processes, and their mere existence does not imply life. Curiosity also uncovered evidence of a habitable ancient lake in Gale Crater, water with a neutral pH containing essential elements for life. Additionally, Curiosity detected puzzling spikes of methane in the Martian atmosphere, brief, localized surges of a gas that, on Earth, is primarily produced by biological processes. These methane detections have sparked controversy. The European Trace Gas Orbiter has been unable to confirm them from orbit. If the methane is indeed real and recurrent, its origin remains a mystery. It could be geological, resulting from subsurface reactions between water and olivine-rich rock. Or it could be biological, stemming from subsurface microorganisms. The enigma persists, yet it adds another layer of intrigue to the question of whether Mars harbors life, not only in its distant past, but potentially in its present, hidden deep underground, shielded from the harsh surface in pockets of liquid brine, warmed by residual geothermal heat. However, curiosity found no definitive evidence of life itself. Perseverance was engineered to push the boundaries of exploration. Its landing site, instruments, and sample collection capabilities were meticulously optimized for the search for biosignatures. Accompanying Perseverance is Ingenuity, a pioneering helicopter drone that made history as the first aircraft to achieve powered flight on another planet. Initially conceived as a 30-day technology demonstration, Ingenuity soared over 70 times during its operational life, acting as an aerial scout that enabled the Perseverance team to pinpoint promising geological targets from above. Unfortunately, it concluded its mission in January 2024 after sustaining damage to one of its blades during its final flight. The triumph of Ingenuity has ushered in a new era of Mars exploration. Future missions may feature more advanced rotorcraft, drones capable of traversing kilometers away from a rover, navigating terrains too rugged for wheeled vehicles, and collecting samples from otherwise inaccessible locations. The thin Martian atmosphere, a mere 1% of Earth's density, presents unique challenges for flight, necessitating blades that spin at over 2,400 revolutions per minute. However, the planet's lower gravity provides some compensation, meaning a Martian helicopter doesn't need to generate as much lift as its Earth-bound counterpart to remain airborne. Perseverance's mission builds upon the discoveries made by its predecessors. Spirit and Opportunity, which landed in 2004, uncovered mineral evidence of ancient water. Curiosity identified organic molecules and a potentially habitable environment. MAVEN studied atmospheric loss, while the Mars Reconnaissance Orbiter mapped the planet with meter-scale precision. Each mission answered critical questions and raised new ones, with every subsequent mission crafted to tackle the mysteries left by those that came before. Perseverance represents the pinnacle of this iterative journey, a mission designed to take that crucial final step, uncovering evidence of life itself. The discovery at Chayava Falls epitomizes this focused endeavor, the most compelling potential biosignature ever identified on another world, achieved through rigorous scientific methodology and published in the world's most esteemed scientific journal. Yet compelling does not equate to conclusive. This distinction is of paramount importance. The annals of astrobiology are strewn with false dawns and hasty proclamations. Scientists have learned, often the hard way, that extraordinary claims necessitate extraordinary evidence. The leopard spots are indeed remarkable. The evidence is robust, but it has yet to reach the level of proof. Proof may hinge on the ability to bring samples back to Earth. However, this endeavor may face hurdles that are not purely scientific, but also political, financial, and logistical in nature. The Sapphire Canyon Tube stands as the most scientifically valuable object on the surface of any planet in our solar system. Yet it may remain untouched for years, or even decades, before anyone attempts to retrieve it. Gateway, in the end, succumbed to its own limitations. This is the simplest and most fundamental explanation. Mars possesses only 11% of Earth's mass and 38% of its surface gravity. Its reduced mass results in a smaller iron core, which cooled more rapidly, extinguishing the dynamo and the magnetic field. Its lower gravity means a weaker grip on its atmosphere, allowing lighter gases to escape with ease. Its smaller size translates to a higher surface area to volume ratio, leading to accelerated heat loss, an earlier end to volcanic activity, and consequently, less replenishment of atmospheric gases. Earth thrived because of its larger size. Its core has remained partially liquid for 4.5 billion years, sustaining the magnetic dynamo. Its stronger gravity has retained a dense atmosphere. The planet's plate tectonics, a process absent on Mars, continuously recycle carbon between the atmosphere, oceans and rocks, ensuring a stable greenhouse effect and a habitable climate. Earth has a built-in thermostat. Mars did not. Yet size alone doesn't paint the full picture. Venus, nearly identical in size to Earth, lacks a dynamo in its core. Meanwhile, the Moon, despite being smaller than Mars, may have briefly possessed a magnetic field in its early days. The intricacies of planetary evolution hinge on a variety of factors: composition, distance from the Sun, timing of impacts, the efficiency of mantle convection, and more, all of which differ from one world to another. Mars's demise was not a result of a single catastrophic event. Rather, it was the cumulative effect of several factors working in concert, making it challenging to pinpoint the most significant one. What stands out is that Mars exemplifies a particular outcome. Among the rocky planets residing in the habitable zone of a Sun-like star, some will be sufficiently large to maintain their magnetic fields, atmospheres, and surface water for billions of years, while others will not. Mars serves as a case study for those that falter, not due to a dramatic catastrophe, but rather through the slow, inexorable consequences of being just a tad too small in a universe that remains indifferent to the requirements of life. Had Mars been a bit larger, perhaps twice its current mass, it might have preserved its magnetic field long enough to shield its atmosphere during the critical early phase when the solar wind was most ferocious. It could still have rivers today. It might still be a candidate for habitability. But it wasn't larger, and thus it perished. There's another crucial factor to consider, one that ties Mars's fate to the very structure of the solar system. Mars's diminutive size may be a byproduct of Jupiter's formation. In early solar system models, especially the Grand Tack hypothesis, Jupiter's inward migration through the protoplanetary disk scattered and depleted the materials in the region where Mars was forming, depriving it of the essential building blocks needed for growth. Had Jupiter formed differently, or not at all, Mars might have accumulated more mass, retained its magnetic field, and remained habitable to this day. From this perspective, Mars was not simply unlucky, it was undermined by the gravitational pull of the largest planet in the solar system, billions of years before the first river carved its surface. The demise of Mars was inscribed in the initial conditions of the solar system, dictated by the mass and movement of a gas giant 400 million kilometers away. This viewpoint is humbling. It implies that a planet's habitability is not solely determined by its own characteristics, its size, distance from the Sun, and composition, but also by the entire architecture of its planetary system. A world can possess all the necessary ingredients and still fail, simply because a distant giant planet altered the arrangement ever so slightly. The habitable zone is not merely a circle drawn around a star, it is a shape sculpted by the gravitational interactions of every body within the system, evolving over billions of years, sensitive to initial conditions that differ from one stellar system to another. Every planetary system is a unique experiment, and Mars is the outcome of our specific experiment. This relevance extends to exoplanets. As astronomers uncover thousands of rocky planets within the habitable zones of other stars, the pressing question arises: how many of these are more akin to Earth, and how many resemble Mars? A planet can possess the right size, be at the right distance, and have the right composition, and still perish if its magnetic field collapses too soon, if its atmosphere is stripped away too quickly, or if its internal heat dissipates before life has a chance to establish itself. Mars serves as a cautionary tale. It illustrates that habitability is not an inherent trait of a planet, but a fleeting condition, a window that opens and closes based on the interplay of internal and external processes. For Mars, that window may have been ajar for around 1.5 billion years. For Earth, it has remained open for at least 4 billion. For exoplanets orbiting more active stars, with stronger stellar winds, that window could be even shorter. Understanding Mars is crucial for grasping the broader question of life's existence in the universe. If planets comparable in size to Mars typically lose their atmospheres and become inhospitable within their first billion years, then the habitable zone around a star is narrower than we previously believed, constrained not only by temperature but also by planetary mass. Only larger rocky planets, like Earth and super-Earths, would remain suitable for life long enough for complex organisms to evolve. The smaller planets would resemble Mars, briefly capable of supporting life before becoming permanently lifeless. This is precisely why the discovery at Jezero Falls holds such significance. If life did emerge on Mars during its fleeting habitable period, it suggests that life can arise swiftly, within a few 100 million years of the onset of suitable conditions. If life can indeed emerge quickly, even planets with short habitable windows, like Mars, could host life, at least temporarily. The universe would not merely be sprinkled with living worlds, but also with lifeless planets that once teemed with life. Graveyards of biospheres that flickered into existence only to be extinguished when their planets could no longer support them. Every planetary system serves as a unique experiment. Mars represents the outcome of our particular experiment, the one that yielded a habitable Earth, an uninhabitable Venus, and a Mars that had its chance but ultimately squandered it. The comparison with Earth is unavoidable. Earth did not escape Mars's fate due to any inherent superiority. It did so because of its mass. By the sheer accident of being slightly larger and heavier, with a core that remained molten for a few billion years longer, Earth avoided the same fate. The distinction between a living world and a dead one is not vast. It is a matter of degree, a factor of 10 in mass, a few 100 million years of dynamo activity. The solar system's habitable zone is not a realm of guaranteed habitability. It is a realm of possibility, and possibility is not synonymous with certainty. Yet, Mars is not entirely devoid of life. The planet experiences weather, though not in the form of rain. Dust storms, driven by seasonal temperature fluctuations, can expand to engulf the entire planet, obscuring the sky and raising surface temperatures by several degrees. These global dust storms occur every few Martian years and can persist for months. They rank among the most dramatic weather phenomena in the solar system, a planet-wide cataclysm of wind-swept dust that would be visible from afar. Mars still boasts polar ice caps that expand and contract with the seasons as carbon dioxide freezes out of the atmosphere in winter and sublimates back in summer. This seasonal cycle induces measurable changes in atmospheric pressure, a planet-wide rhythm of inhaling and exhaling carbon dioxide, dictated by the tilt of its axis. There may be liquid water lurking beneath the surface. Radar observations from the Mars Express and Mars Reconnaissance Orbiter have identified reflective layers beneath the southern polar ice cap, which some researchers interpret as bodies of liquid brine. This interpretation is debated. The reflections might be due to specific types of clay or other minerals, but the possibility of subsurface liquid water on Mars remains on the table. If it exists, it would be extremely cold, highly saline, and incredibly hostile to life as we know it. Yet, it might not be entirely devoid of life. Moreover, Mars still exhibits volcanism, or at least the potential for it. InSight, NASA's Martian seismometer mission, which operated from 2018 to 2022, was the first mission dedicated to studying the deep interior of Mars. Its seismometer, SEIS, detected over 1,300 Marsquakes during its operational period, confirming that Mars is seismically active and providing the first direct measurements of the planet's internal structure. The findings were nothing short of groundbreaking. InSight revealed that Mars's core is liquid, with a radius of approximately 1,830 kilometers, larger and less dense than scientists had anticipated, indicating it harbors considerable amounts of light elements such as sulfur, oxygen, and hydrogen mixed with iron. The mantle consists of a single convecting layer, lacking the intricate stratification found in Earth's mantle. Meanwhile, the crust is thicker than previously estimated, averaging about 25 to 50 kilometers, with the southern highlands exhibiting a notably greater thickness compared to the northern lowlands. The seismic data further confirmed that Mars's core is entirely liquid. There is no solid inner core, or at least none that InSight's instruments could detect. This is crucial because on Earth, the solidification of the inner core is a key driver of the dynamo effect. If Mars's core never formed a solid inner core, or if it solidified completely, this could explain the shutdown of its dynamo. The state of Mars's core is intrinsically linked to the mystery of why its magnetic field faded away. Among the Marsquakes that InSight detected before its mission concluded in 2022 were seismic waves traversing the planet's interior, originating from a region near the Cerberus Fossae fracture system. Some of these seismic events may have been triggered by residual volcanic or tectonic activity. The mantle could still harbor pockets of partially molten rock. Olympus Mons might not be as dormant as it appears. Mars is not a static, frozen entity. It is a planet in the twilight of a slow decline, still twitching, still evolving, still losing its atmosphere to the void of space, still reshaping its polar ice with the changing seasons. The process of decline is not complete, it is ongoing. The remnants of Mars's former self, the ice, the minerals, the sedimentary rocks, the ancient river valleys, are preserved with a clarity that Earth, with its active plate tectonics and water cycle, could never replicate. In a way, Mars serves as the solar system's most remarkable archive of early planetary habitability. The very forces that led to its demise also safeguarded its history. This is precisely why we explore Mars with such fervor. Not because it is teeming with life, but because it holds the memories of a time when it was. Every rock that Perseverance drills into, every mineral that Curiosity analyzes, every atmospheric measurement taken by Maven tells a story from the diary of a world that once had everything and lost it all. And among those stories, sealed within a titanium tube on the floor of Jezero crater, there may be a sentence that reads, "Life was here." Now, step back from the mineral compositions, isotopic ratios, and orbital mechanics, and reflect on what Mars truly signifies. Here is a planet that was born with all the essential ingredients for life: water, warmth, chemistry, energy, and a magnetic shield to protect it all. For perhaps 1.5 billion years, these elements coexisted on the surface of a world that was, by all measures, habitable. Rivers flowed, lakes thrived, deltas formed. The chemical energy was present, the elements were available, the time was ample. And then it came to an end. Not due to a cosmic disaster, but because the planet was too small to sustain the internal processes that kept it alive. The core cooled, the dynamo ceased, the shield collapsed, the atmosphere was stripped away, the water disappeared. What remained was a cold, dry, irradiated world that holds within its rocks and dust the memory of everything it once had. If life did emerge on Mars, if the peculiar patterns in Chayava Falls are indeed what they seem, the implications are monumental. It would suggest that life arose independently on 2 neighboring planets within the same solar system, within the first billion years of their existence. It would imply that the origin of life is not an extraordinarily rare event, but a natural process that readily occurs when conditions are favorable. And it would mean that the universe, with its billions of rocky planets in habitable zones around countless stars, is almost certainly brimming with life. If life never emerged on Mars, if the enigmatic spots we observe are merely the result of non-biological chemistry, the ramifications would be equally profound. It would suggest that habitability alone isn't enough. A planet can possess water, warmth, chemistry, and time, yet still remain desolate. The genesis of life must involve something beyond these elements, a threshold, a catalyst, or perhaps an unforeseen accident that remains a mystery to us. This realization would render Earth's biosphere even more precious, improbable, and solitary. Regardless of which scenario unfolds, everything changes. And the answer might be nestled within a titanium tube, resting on the floor of an ancient lake, 225 million kilometers away from the nearest lab capable of deciphering it. Mars stands as the solar system's most captivating mystery. A world that once had it all, lost it all, and left behind a crime scene so meticulously preserved that 3.5 billion years later, we can still decipher the clues. The weapon? The relentless solar wind. The motive? Indifference. The cold, mechanical apathy of a universe that shows no concern for whether worlds can support life, that neither intentionally nurtures nor extinguishes existence, but simply adheres to the laws of physics as they unfold. And the victim? The victim may have been more than just a planet. It could have been a biosphere, a second genesis, a community of organisms, however rudimentary, that thrived, metabolized, and perished in the silt of Martian rivers, leaving behind, in a solitary rock within a single riverbed, patterns that would be recognizable to a geochemist from another world, 3.5 billion years hence. We do not yet know. The data is tantalizing but incomplete. The sample has been collected but remains unreturned. The question, the oldest, deepest, most consequential question in all of science, remains unresolved. Have we ever been alone? Mars holds the key, or at least it offers the next clue. Somewhere within the rust-red dust of Jezero crater, encased in a titanium tube, a small fragment of ancient river mud patiently awaits someone to come and unveil the message it has carried for 3.5 billion years. The message might reveal nothing, or it could encompass everything. There exists a profound asymmetry in the potential answers. If the spots are biological, if Martian microbes once thrived by metabolizing iron in the mud of Jezero's rivers, then the implications radiate outward in every direction. Life emerged twice within a single solar system. The chemical processes that give rise to living organisms are likely common, natural, and perhaps inevitable wherever conditions are favorable. The universe, with its trillions of rocky planets in habitable zones, is almost certainly teeming with life. Conversely, if the spots are not biological, if they stem from some exotic chemistry that mimics life but is not life, then we glean something equally valuable. We learn that the universe can produce false positives. That chemistry can imitate life with astonishing accuracy, and that distinguishing between life and non-life, even when holding the rock in your hands, is one of the most challenging dilemmas in all of science. In either case, Mars has offered us something no other planet has, a testable hypothesis regarding extraterrestrial life. Not mere speculation, not inference, not a statistical argument about the likelihood of life existing somewhere in the cosmos. A specific rock from a specific location with specific features, gathered by a specific instrument, sealed in a specific tube, awaiting specific laboratory analysis. For the first time in history, the question of life beyond Earth has been distilled into a practical engineering challenge. How do we bring that tube home? And perhaps this is the most profound legacy of our quest to explore Mars. It's not merely about the answers we have yet to uncover, but rather the questions we've framed with such clarity and rigor that they stand ready to be answered. Science doesn't advance by simply providing answers in a vacuum. It thrives by transforming questions into those that can be addressed. Mars has brought us closer than ever to answering the most ancient of inquiries. All we need to do now is reach out and seize it. With each passing moment, we risk losing more than just the samples, which will remain preserved in their titanium containers for eons. We stand to lose the context. The scientists who crafted this mission, who meticulously selected the landing site, who navigated the rover to Chayava Falls, and who discerned the significance of the leopard spots, they won't be around forever. Institutional memory fades, teams scatter, expertise dissipates. While the samples may endure, the human insight required to interpret them is fleeting. Yet, there's an even greater urgency at play. Mars is the only planet in our solar system where we have pinpointed a specific, testable candidate for signs of past life. If we neglect to act on this discovery, if we let the samples linger on Mars while we engage in debates over budgets and timelines, we will have come closer to answering the question of life beyond Earth than any generation before us, only to turn away at the last moment. The universe isn't obliged to make its mysteries easy to uncover. It has placed the closest and most accessible candidate for extraterrestrial life on a planet that, on average, lies 225 million kilometers from the nearest laboratory. It has safeguarded potential biosignatures within rocks that are 3.5 billion years old, preserved by their own aridness and the frigid, airless environment that extinguished the world that birthed them. And it has equipped us with the technology to reach those rocks, identify the signatures, collect the samples and, if we choose, bring them back home. The decision lies with us. The universe has played its part. The rest is up to humanity. 4.5 billion years ago, two neighboring planets revolved around a youthful star. Both possessed water, both had atmospheres, both contained the essential chemistry for life. One was slightly larger, the other slightly smaller. The larger planet retained its magnetic field, its atmosphere, its water, and eventually gave rise to forests, oceans, cities, and mines capable of constructing robots to send to the smaller planet to inquire what went awry. The smaller planet lost its magnetic field. It lost its atmosphere. It lost its water. It lost everything, except perhaps the remnants of whatever thrived there during its fleeting window of habitability. Those remnants, if they exist, are encased in ancient sedimentary rocks within a long-extinct crater on a lifeless world, sealed in a tube, awaiting discovery. The chasm between these two destinies, a vibrant world and a lifeless one, was not insurmountable. It hinged on a factor of 10 in mass, a few 100 million years of dynamo activity, and a slightly larger iron core. The distinction between Earth and Mars is not one of kind, it is a matter of degree. And that subtle difference made all the difference. Mars is not simply a barren planet, it is a reflection. It reveals what our world could have become and what it managed to avoid becoming, through nothing more than the serendipity of being born just a bit larger in a solar system indifferent to outcomes. And somewhere, in the delicate butterscotch-hued twilight of a Martian afternoon, a small rover rests beside a rock adorned with leopard spots, its drill hole visible, its sample sealed, its mission accomplished. It has posed the question, it has gathered the evidence, it has fulfilled its purpose. The answer lies within the tube, and the more attentively we listen, the more it has to share,